Hello, my name is Mattias Edberg and I am the creator of NETAN RAN. Over the past 25 years, I have been working at the intersection of RAN architecture, IP/MPLs, optical and microwave transport networks, and analytical/simulated performance modeling. NETAN RAN is the result of that work, a deterministic digital twin for 5G and future 6G networks, integrating both radio access and transport into one unified performance model. It combines analytical computation with time-domain simulation, allowing us to move from design assumptions to measurable, quantifiable network behavior. Here, I'll show you how this model bridges RAN and transport, and why that integration is critical for predictable end-to-end performance. Slide 2. Why end-to-end modeling matters. Modern 5G and emerging 6G networks are no longer best effort systems. We are now supporting latency-sensitive services, industrial automation, critical communications, real-time control, where milliseconds truly matter. At the same time, traffic behavior has become highly volatile. Flows fluctuate, burst patterns shift, and utilization can spike unpredictably across both RAN and transport domains. Under overload conditions or partial failures, classical silo-based models often fail to predict the real impact. What looks acceptable in RAN may collapse in transport, or vice versa. And as automation and AI-driven control become more common, we face a new risk: automation without deterministic validation. If we cannot quantify delay variation, and loss end-to-end under stress, we are effectively flying blind. Slide 3. What NETAN RAN is. NETAN RAN is an integrated RAN and IP/MPLs transport performance model. It treats radio and transport as a single end-to-end system, where delay, jitter, and loss accumulate across domains. At its core, the platform contains two complementary engines. First, a deterministic analytical engine that computes queuing delay distributions, loss probabilities, and utilization under defined what-if traffic and capacity conditions. Second, an event-driven time-domain simulator that models burst-level behavior, traffic volatility, overload dynamics, and failure propagation across the network. Because the simulation is event-driven rather than purely time-stepped, it can accurately represent flow interactions and transient behavior under stress. Events like traffic spikes, link or site failures, traffic rerouting, and radio fading can be simulated. Together, this forms a deterministic digital twin, not only for performance validation, but also as a controlled training environment for AI and ML-based network control. Instead of training automation on live networks, we can generate reproducible stress scenarios, measure outcomes, and validate control strategies before deployment. Slide 4. RAAN and transport integration. What you see here are analytical results computed separately for the RAN domain and the transport domain. In the left column, we analyze the transport network. These plots show how transport links across the network are loaded and the corresponding average queuing delay they introduce. The upper plot represents prioritized UDP traffic, while the lower plot shows best effort TCP traffic with lower scheduling priority. In the center column, we perform the same analysis for the RAN domain across radio cells and sites. Again, we observe how increasing utilization drives nonlinear growth in queuing delay, separately for prioritized and best effort traffic losses. And in the right column, we see the physical network view. Here, radio sites and transport links are visualized geographically, color-coded by their mean utilization. This connects analytical performance results directly to the real physical network structure. The key takeaway is that delay behavior is not abstract. It is anchored in actual topology and load distribution. Slide 5. Analytical engine. In the previous slide, we looked at average queuing delay. But mean values hide tail behavior. What you see here are full delay distributions, both the probability density function, PDF, and the complementary cumulative distribution function, CCDF, for prioritized UDP and best effort TCP traffic. On the left, we analyze transport paths only. The upper row shows UDP delay distributions, and the lower row shows TCP delay distributions under different load conditions. The CCDF view is particularly important because it reveals tail probability, the likelihood that delay exceeds a given threshold. In the center column, we perform the same analysis for the RAN domain across radio sites and cells. And on the right, we combine radio and transport effects into true end-to-end delay distributions. Here, we clearly see how tail probabilities compound across domains. Small nonlinearities in each domain accumulate, directly affecting packet loss thresholds, SLA compliance, and user experience. Part 6. Simulation. What we are seeing here is a 10-second simulated network scenario, executed with 1 millisecond time resolution. The playback takes approximately 50 seconds, but internally, the system models burst level behavior at millisecond granularity. The scenario is divided into 3 phases: steady state, transport reconfiguration with moderate load increase, and finally, high stress overload conditions. During the first 5 seconds, the system operates under steady state conditions. On the left, the topology view shows link utilization and air interface utilization at access sites. Utilization is stable and well below saturation. In the upper right graphs, loss remains near zero and delivered load closely follows offered load. Buffer levels in both transport and RAN remain controlled. Median buffer occupancy is stable and maximum values are limited. End-to-end delay distributions reflect predictable behavior. Low median delay for UDP, moderate delay for TCP, and controlled tail behavior. In short, the system behaves linearly and predictably. At 5 seconds, 2 events occur simultaneously. First, traffic is redirected from primary transport paths to backup paths. Second, air interface traffic increases by 20% across all cells. Immediately, we observe a shift in utilization patterns on the topology view. Some transport links become more heavily loaded due to the backup routing configuration. In the buffer graphs, transport maximum buffer occupancy increases sharply, indicating transient congestion. The utilization plots show increased median and maximum values across both links and cells. End-to-end delay increases, particularly for TCP traffic, as queuing effects begin to compound. At 7 seconds, load increases further, now reaching 60% above the original baseline. The system transitions from stress into overload conditions. Transport maximum buffers rise sharply, and we observe clear divergence between median and maximum behavior, indicating localized congestion. Loss begins to accumulate, particularly in transport, as buffers exceed threshold limits. Delivered load no longer follows offered load perfectly. We see performance degradation. End-to-end delay increases significantly, especially in the TCP2 class, where tail delay exceeds buffer tolerance thresholds. The purpose of this simulation is not simply to show overload. It is to demonstrate that deterministic modeling allows us to observe, quantify, and predict these transitions before they occur in production networks. Instead of reacting to incidents, we can model stress propagation and validate control strategies in advance. Slide 7. What this enables. First, capacity dimensioning. Instead of sizing networks based on average load assumptions, we can dimension based on delay distribution and tail probability. This means provisioning capacity not only for expected traffic, but for nonlinear queue growth under stress. The result is smarter investment decisions and reduced over-provisioning. Second, resilience testing. We can simulate path failures, traffic rerouting/uptake scenarios, and traffic surges, and observe how delay, buffers, and loss evolve in real time. This allows validation of backup path design and margin before incidents occur in production networks. Third, failure impact quantification. Instead of describing impact qualitatively, we can quantify it. How much additional delay? How much loss probability increase? Which traffic classes are affected? This transforms incident planning from reactive troubleshooting into predictive engineering. And finally, automation validation and AI training. AI-driven network control must be trained and validated under controlled stress scenarios. NETAN RAN provides deterministic ground truth performance data, enabling safe evaluation of load balancing, path selection, and traffic shaping strategies before deployment. This reduces operational risk while accelerating autonomous network evolution. Summary. For decades, networks have been designed based on assumptions: average load, estimated margins, best effort resilience. But modern networks no longer behave linearly. They operate under volatility, dynamic routing, and strict latency constraints. At the same time, we are moving toward automated and AI-driven control. Yet, automation without deterministic understanding introduces risk. What NETAN RAN offers is not another monitoring tool. It offers measurable causality. It allows us to understand before deployment how delay distributions evolve, how failures propagate, and how control decisions reshape performance. It provides the controlled environment where automation strategies can be validated and where AI/ML models can be trained against deterministic ground truth. From design assumptions to deterministic quantifiable behavior, from reactive troubleshooting to engineered confidence, from static configuration to validated intelligent network control. This is the foundation for resilient 5G and autonomous 6G systems.